What's going on, guys? So apologize for my appearance, and I'll probably do it in every video because at least the ones that I make tonight. But it's late, and I'm tired, and I don't feel like changing. I was just at the gym. I'm gonna work through a couple of these problems with you guys, just so you can see. I mean, I know you have the solutions guides, but that's not always quite enough. So let's go through these real quick. So this is 2019, the second option or the second version, number 3. We have 2 plates, set up potential difference V between them. Small sphere of mass M and charge minus E is placed on the left-hand plate, which has a negative charge allowed to accelerate across the space. So our particle of mass M, charge E, is going to accelerate across from the negative plate to the positive plate, right? We can see that this one's going to end up negative. This one's going to end up positive because of the orientation of the potential difference there. After passing through the opening, enters a region where the uniform magnetic field, magnitude B, directed into the page. You can see that with all the X's there. Ignore gravitational effects. Express all algebraic answers in terms of V, M, E, B, and fundamental constants. All right, so what is the initial direction of the force on the sphere as it enters the magnetic field? So if we look at our particle here, right, it's going to enter the magnetic field at this point, traveling in this direction. So if we look at our right-hand rule, right, traveling to the right, magnetic field is towards the computer. That obviously leaves my thumb pointing up. But because this is a negative particle, we have to reverse that. So the force actually ends up being down originally. So our particle, immediately after entering the field, here's a force that is towards the bottom of the page. So there's our first answer right there, towards the bottom of the page. Real easy right-hand rule. Describe the path taken. So this is kind of one of those interesting things about particles in magnetic fields. They always, as long as everything's perpendicular, right? Which in this case it is like purely perpendicular, right? This is going to the left, magnetic fields into the page. They'll travel in circles. So this particle, as it enters the field, it's going to feel a force down, which is going to bend its path back towards the beginning. And we get this semicircle right here as our particle travels through the magnetic field. Now, as soon as it leaves the magnetic field, right, it'll keep traveling straight. But until that point, it's going to travel in a semicircle or a circular path. So describe the path taken. It's going to be a circular path toward the bottom of the page. Apparently it doesn't like to draw O's right now. Oh, I have ink to shape on. It's trying to make shapes out of the things that I'm writing. So it turned them into lines. Interesting. All right, well, glad that I noticed that now. Derive an expression for the speed of the sphere as it passes through the small opening. So the sphere, as it passes through the opening, right, it's gaining energy, kinetic energy, as it moves across our potential difference here. So this actually has nothing to do with a magnetic field, right? It's just a parallel plate capacitor, and we are accelerating our charge across. So we have a conservation of energy problem here, where we're going to end up with the potential difference or potential energy, which is going to be negative because we're going from the negative plate to the positive plate, right? We're going final minus initial. We end up with larger potential or a more positive potential at the positive plate. So we end up with a negative when we look at our potential difference there, is equal to our kinetic energy. So we're going to get, if you look up potential energy equation, we get QV. So we're going to minus QV equals 1/2 mv squared. The charge Q is actually E in this case, right? It says we got to use V, M, E, and B. So we replace that with a negative E. It actually says it's negative E. So we get negative, negative gives us positive. So we get EV equals 1/2 mv squared. And then we just solve for V. So 2 goes over, m goes underneath. We take the square root, and we get the velocity is stinking dogs, square root of EV, 2EV over m. There we go. All right. Derive an expression for radius. So our next step is to derive an expression for radius. This one we're actually going to use centripetal force equation. So our magnetic force is acting as a centripetal force because it's causing our particle to go in a circular motion. So we can take our magnetic force equation, QVB equal to, this is lowercase v velocity, equal to sorry, I forgot for a second, mv squared over r. And then we're solving for r, right? We want an expression for radius, so we have to solve for r. So velocity will cancel with one of the velocities there. R comes across, QVB goes over, so we get R is equal to MV over Q. Actually, I should write that as E, right? Because this is going to be an E. EB. All right, so that kind of sets us up. But again, it wants it in terms of V being potential, not velocity, M, E, and B. So we got to substitute in our velocity here. So we'll get R equals M over E, B. I don't know why I wrote that lowercase b. It should be capital B, times the square root of 2EV over M. And then we could bring some of that stuff in to the equation to kind of simplify a little bit, right? We can bring in an M squared, which will cancel with one of the M's. We can bring in an E squared, which will cancel with this E. We could bring in a B squared. All right, we could actually put everything under the square root there just to kind of clean it up. So we'll have 2mv being potential, which is allowed, over E B squared. And there is our expression for radius. And I think I got everything. M cancels M on top. 2 E cancels with the E squared on the bottom. So we get an E on the bottom. We get a B squared on the bottom. B stays on top. Yep, I think I got everything. There we go. Expression for radius. All right, so now we come to the second part. Experiment performed with which, hey, sorry, my dog just brought a toy into the room and he's squeaking it. Knock it off. Beam of electrons accelerated across space between plates, passes through small opening. Hey, bro. Sorry, I didn't mean to scare it, but I know you haven't heard me yell before. But electron traveling semicircular path, strike the right-hand plate. Potential difference between places varied at regular increments. For each potential difference, the magnetic field is varied in order to cause the beam to strike. Stop. You lost your privileges. Cause the beam strike right-hand plane, distance of 0.2 meters from the opening. All right, so this one tricked me a little bit, especially when we get down to part D here. We are actually keeping the right hand or this distance from the opening constant, and that messed me up the first time I went through this problem. So that's something to kind of keep in consideration, right? The beam is always going to strike a distance of 0.02 meters from the opening, which means R is going to be constant, which I messed up the first time I went through this. So indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate numerical value for mass to charge ratio of an electron. So if we look at the equation we just derived, right, R equals the square root of 2mv over EB squared, right? What we want is this as our slope. That is the mass divided by charge, right? The mass to charge ratio of our electron. So initially what I was thinking, well, okay, I'll just square both sides, right? So we get R squared equals 2mv over EB squared, right? And then I'll just plot R squared with 2VB squared, right? And then that'll give me a graph that shows what I need, right? ME would end up being the slope there. Problem with that is R is a constant, which means we can't set it up as one of our variables. It's not varying. It doesn't make sense. So we actually have to switch the R and the B here. So I'm going to switch B squared over here. So B squared equals, I'll put ME together so we know our mass and charge ratio is there. And then we'll get 2V over R squared, right? And then if we plot B squared with 2V over R squared, right, our slope will end up being M over E. So my vertical axis is going to be B squared. My horizontal axis is going to be 2V over R squared. And this isn't the only way to do it. I think if you look at the solutions or the answer key, it puts just potential here, right? Just V, which gives you a slope of 2M over ER, 2M over ER. And then they found a value for the slope and then solved for M over E. The way that I did it, when I actually calculate the slope will be M over V. But it means I have to add another little section here to my table. So I'm calculating vertical axis B squared. So I need B squared, which is going to be in Tesla to the -3rd squared. And I also need 2V over R squared, which is going to be in volts per meter squared, and it's actually going to end up being times 10 to the 6th. Because we're dividing by R squared is a really small number there. We end up getting really large values for our for this number right here. So I wrote these numbers down so that I didn't have to calculate them on the spot here. So we get 6.68, 7.73, 11.5, 12.5, 14.3, and 15.9. And then 2V over R squared, I ended up with 1.2, 1.4, 2.0, 2.2, 2.4, and 2.8. All right, so that's just 120 divided by R ends up being 0.01. So R squared is 1 times 10 to the -4th. So 120 divided by 1 times 10 to the -4th gives us 1.2 times 10 to the 6th, 1.2 million as the value there. So I included those. I labeled each column, right, with the units I was going to use as well. I actually graphed this ahead of time so that you guys didn't have to sit and watch me try and graph all of these points out. But bottom goes by 1 every 10. I started this one at 4. It didn't say anything against having a break in your graph or not starting at 0. And it helps to kind of give a better view of the line than to try to make it go from 0 to 16 evenly, because it just doesn't work real well. Then I pick 2 points, right, using straight line. Oh, wait, on the graph, plot the relationship, which I did. Label the axes, which I did, including units, which they have. Draw a straight line right here, and then use the straight line to determine the mass ratio. So all I have to do is determine the slope of that line. And I picked 2 points. I'll highlight them in red so that you can see them a little bit better. I picked this point right here, and where's my second point? I think it's this one right here. And if we look at those points, rise over run, right? Y2 minus Y1, that's 14.4 minus 8.4 over 2.5 minus 1.5. And we get, obviously this one's times 10 to the negative sixth. This one's times 10 to the positive sixth. So we'll get 6 times 10 to the negative sixth divided by 1 times 10 to the positive sixth. And I end up with an answer of 6 times 10 to the 12th. And I just wrote it's going to be kilograms per coulomb, right? I don't know if that works. I mean, I guess technically based on the numbers I divided, I would get Tesla meter squared per volt, which I guess ends up as, right, I would get Tesla meter squared per volt, which I guess simplifies to kilograms per coulomb. But, right, I just assume because it's a charge to mass ratio, mass to charge ratio, we get something like that. Doesn't ask us to prove it, so I guess we don't have to. If you wanted to, I guess we could take 9 times 10 to the 9.11 times 10 to the negative 31st and divide that by, right, mass to charge. Divide that by 1.6 times 10 to the negative 19th, and we get 5.69 times 10 to the negative, so 5.7. So I was a little bit high. Actually, this is a negative 12th. I don't know why I missed that, but I was a little bit high on my estimation. We get 5.7 as opposed to 6.0, but it doesn't ask us to compare to anything, so I think we're good with that. All right, and there is problem 9, or from 2019, problem number 3. Let's stop this recording.